Welcome to The Deep Dive. Today, we're tackling something truly mind-bending, black holes. These things, they just stretch our understanding of, well, everything, gravity, space-time. We're talking about these invisible cosmic monsters, right? Regions where space-time is so warped, so crushed, that literally nothing escapes, not even light. They can twist space, warp time, swallow whole stars. It's pretty wild stuff. So for this deep dive, our mission is basically to unpack these bizarre objects. What are they? How do they even form? And, what happens if you get too close? We'll even touch on their role in the bigger cosmic picture. Let's start right there. What is a black hole, fundamentally? Because they seem, well, impossible, almost.
They really do push the limits, don't they? But the core idea, it comes straight from Einstein's theory of general relativity. Essentially, a black hole is an extreme distortion, a warping of space-time itself. Imagine space-time as a kind of fabric. A black hole is where that fabric is pulled down so intensely, so profoundly, that it creates this region you can't get out of. Light gets trapped. It's like gravity's ultimate victory. Its pull just overwhelms everything.
Okay, so it's not just some massive object sitting in space. It's space itself being altered. Is that the key idea?
That's a really crucial distinction, yeah. It means we're dealing with something fundamental about reality, not just a big, heavy thing. Think of it like this, maybe. Imagine space is flowing like a river. A black hole is where that river starts flowing incredibly fast, faster and faster towards a central point. And once you cross a certain line in that river, the current is too strong. No matter how fast you swim, you get pulled downstream.
Okay, that river analogy, that helps. And how do these things usually form? You mentioned stars.
Right? The classic example, the most common way we think they form, is when a really massive star runs out of fuel at the end of its life. It collapses under its own gravity, catastrophically. And if it's massive enough, nothing can stop that collapse.
That makes sense. But it still feels abstract. How did we go from that idea to actually, figuring out these invisible extreme things even existed? It wasn't like we could just see them initially.
No, definitely not. And that journey, the discovery, it's fascinating. The mathematical seeds were planted surprisingly early. We're talking 1916, just months, literally months, after Einstein published general relativity.
Seriously? That early?
Yeah. A physicist named Carl Schwarzschild, he found a solution to Einstein's equations. It described how space-time gets warped around a perfectly spherical, non-spinning mass. Like the math for a simple star.
Just calculating the gravity around a star, then.
Pretty much. But here's the kicker. The equations he found, if you sort of hypothetically kept the warping described by the math, but took away the actual star.
Remove the matter itself.
Exactly. Removed the matter, but kept the mathematical distortion. What you were left with was a perfect description of a non-spinning black hole. It was hiding in the math all along.
Wow, so the theory was they're decades before we had any real clue they might actually be out there. That's amazing, really. Pure math leading the way.
It really is. And it gets wilder. If you push that 1916 math to its limits, its theoretical extremes, it didn't just describe black holes. It also had hints of what we now call wormholes, like an Einstein-Rosen bridge connecting different points in space-time.
Yep.
And even white holes, maybe other universes.
White holes, like the opposite.
Sort of, yeah.
Yeah.
Things could only come out, not go in. Highly theoretical. But the point is, these concepts were embedded in the physics right from the start.
Right.
But then came the big debate, into the 1930s. Could nature actually make these things? Even Einstein was skeptical for a while.
Right, the math is one thing, but can reality actually do that?
Exactly. The proof of concept that nature could do it came just before World War II. A really important paper by Oppenheimer and Snyder. They showed that under certain assumptions, if a star is massive enough when it collapses, its gravity will just overwhelm everything. Nothing can stop it. Once it passes certain limits, you might hear names like the Chandrasekhar limit or the Oppenheimer-Tolman limit. The collapse is unstoppable. It has to form something like a black hole, a singularity.
So that was the theoretical proof that it's possible.
Pretty much, yeah. It showed nature had a pathway. Then, later work, like Roger Penrose in the 1960s, really firmed up the theory of how collapse leads to singularities. And around the same time, Roy Kerr found the solution for spinning black holes, which are more realistic but built on those same core ideas.
Okay, let's get back to that river. You mentioned a point of no return, the event horizon, right? What actually happens there?
Right, the event horizon. Using that river model again, imagine space flowing into the black hole. As you get closer, that river of space flows faster and faster. The event horizon is the precise point where the river of space is flowing inwards at the speed of light.
At the speed of light. So if you're right on the horizon, even light trying to escape can't make progress.
Exactly. Think of a fish swimming upstream against a current. If the river flows at exactly the speed the fish can swim, the fish just stays in place, right? Relative to the riverbank anyway. Light emitted right at the event horizon trying to get out is like that fish. It's frozen there, stretched out, unable to escape the inward flow of space itself.
And if you cross it?
Once you're inside, the river of space is flowing inwards faster than light speed. So no matter what you do, no matter how powerful your rocket, you can't swim against that current. You are inevitably swept inwards.
Towards the center, towards the singularity.
Towards the singularity, yes. But here's where it gets really weird again, and it's a common misunderstanding. In general relativity, the singularity isn't really a place in space you can point to.
Not a tiny point.
Not exactly. It's better described as a moment in time, an inevitable future moment.
A moment in time. How does that work?
Think about tomorrow for us, right now. Tomorrow is in our future. No matter what we do today, where we go, we can't avoid reaching tomorrow. It's an inevitable future time. Once you cross the event horizon of a black hole, the singularity becomes like your tomorrow. It's a future moment you are destined to reach, no matter which way you try to move in space. Space and time get so warped inside that they essentially swap roles. Your movement through time becomes movement towards the singularity.
Okay, my head hurts a little now. Space and time swapping roles. But even with all this weirdness, this light-trapping nature, we do have solid evidence they exist, right? This isn't just theory anymore.
Oh, absolutely. The evidence is incredibly strong now. Rock solid, really. I mean, there's the gravitational evidence. Observing stars orbiting something invisible at the center of our own galaxy, the Milky Way, we call that object Sagittarius A, or SGRA for short. The way those stars whip around it, you can calculate the mass and size of the object they're orbiting. It has to be something incredibly massive, millions of times the mass of our sun, crammed into a tiny space. And we can't see it. That work actually won a Nobel Prize recently.
Because the gravity gives it away, and then we actually managed to see them, sort of, the images.
Exactly. The Event Horizon Telescope Project.
Yeah.
Groundbreaking stuff. They used a network of radio telescopes around the world, essentially creating an Earth-sized telescope to get actual images. We have images of the shadow of the black hole at the center of the M87 galaxy. That one's huge, like 6 billion times the sun's mass.
Yeah.
And also our own SGRA. You see this dark central region, the shadow, surrounded by the glowing hot gas swirling around it just before it falls in. It's direct visual confirmation.
Incredible. So we have stellar mass ones from collapsed stars, and then these monsters at the center of galaxies, supermassive black holes. What's the deal with them?
Yeah, the supermassive ones are a whole other level. Millions, sometimes billions of times the mass of our sun. And we think pretty much every large galaxy, including ours, has one lurking at its core. They're not just sitting there either. They really dominate their galaxies. They influence the orbits of billions of stars. They shape how galaxies evolve over cosmic time. They can spew out enormous jets of particles and radiation that stretch for millions of light years. When they're actively feeding, they can outshine their entire host galaxy.
So they're like cosmic engines, in a way, not just sinks.
Definitely. Cosmic engines, cosmic architects, they play a huge role. But how they got so big, especially so early in the universe, is still a bit of a puzzle.
How do they think they formed?
Well, smaller black holes merging together over time probably contributes. But to get so big so fast, the leading idea now is something called direct collapse. The idea is that very early on, shortly after the Big Bang, maybe huge clouds of pristine gas collapsed directly into massive black hole seeds, bypassing the whole star phase. But the models for how these early galaxies and their central black holes grew together, well, that's still being worked out. It's a hot area of research, especially with telescopes like James Webb, giving us new clues about the early universe.
Okay, let's get to the question I know everyone listening is thinking about, the sci-fi staple. If you fell into a black hole, would you really get stretched into spaghetti? Is spaghettification real?
Ah, yes. Spaghettification. It sounds gruesome, and it is real. It's caused by tidal forces.
Tidal forces, like the ocean tides.
Exactly the same principle, just ramped up to extreme levels.
Yep.
Tides happen because gravity pulls differently on different parts of an object. The moon pulls slightly harder on the side of Earth facing it than the side away from it, stretching the oceans. Near a black hole, the difference in gravitational pull between, say, your feet and your head becomes enormous. Your feet get pulled much, much more strongly than your head.
So you get stretched out, like spaghetti.
Pretty much. Now, here's a really interesting twist, though, something most people don't realize. It depends on the size of the black hole.
Oh, how so?
For a stellar mass black hole, maybe 10, 30 times the mass of the sun, those tidal forces become incredibly strong before you even reach the event horizon.
Yeah.
So yeah, for those smaller ones, you're definitely getting spaghettified before or right as you cross the point of no return. It would be unpleasant.
Okay, good to know. Avoid the small ones. What about the supermassive ones?
This is the counterintuitive part. For a supermassive black hole, millions or billions of times the sun's mass, the event horizon is much, much larger. It's further out from the central singularity. Because it's so much larger, the difference in gravity across your body at the event horizon is actually quite small. The tidal forces are surprisingly weak there.
Wait, really? So you could cross the event horizon of a giant black hole and be okay, initially?
According to Einstein's theory, yes. You could free fall across the event horizon of a sufficiently large supermassive black hole, and at that moment, notice absolutely nothing unusual, no immediate spaghettification.
That is completely unexpected. Why the difference? Just the scale.
It's the gradient, the rate at which gravity increases as you get closer. For a small black hole, gravity ramps up incredibly steeply over short distances. For a supermassive one, the slope is much gentler at the horizon. Think of it like falling off a gentle curve versus falling off a sharp cliff edge. The eventual outcome is the same, but the initial experience is different.
So you cross over feeling fine, but the end is still coming, right? The singularity.
Oh, absolutely. Don't get too comfortable floating past the event horizon. The singularity is still inevitably in your future. Depending on the mass of the black hole, you might have maybe hours, perhaps even a day or so inside, before the tidal forces become overwhelming. But eventually, they will become overwhelming. You'll get stretched vertically, squashed horizontally, your atoms ripped apart, and then you reach the singularity.
Which, in Einstein's theory, is the end of time, as you said.
Right, that's what classical general relativity predicts.
Yeah.
But then Stephen Hawking came along in the 1970s with his work combining general relativity and quantum mechanics. He showed that black holes aren't perfectly black. Due to quantum effects near the event horizon, they actually radiate particles, Hawking radiation. It's incredibly slow for large black holes, but it means they lose mass and energy over truly vast timescales. Eventually, they should completely evaporate.
So they don't last forever. Everything gets back out eventually.
In a very, very scrambled form, yes. It suggests that maybe the end of time, the singularity, isn't the absolute final word. Information, in some sense, might return to the universe. It's still debated exactly how that works, mind you.
Okay, final stretch here. Let's think big picture. How big can these things get? Is there a limit? And this wild idea, could our whole universe be inside a black hole?
In terms of maximum size, there's no known fundamental upper limit from physics itself. It seems to be limited just by how much matter was available to feed them, especially in the early universe. The conditions right after the Big Bang, the initial distribution of stuff, quantum fluctuations during inflation, that's at the stage. We see black holes now that are tens of billions of times the mass of the sun. Maybe they can get even bigger.
And the universe in a black hole idea, or black holes as gateways.
That's definitely out there on the edge of speculation, but it connects to some deep ideas. Some theories explore whether the conditions at a singularity inside a black hole could somehow trigger something like a new Big Bang, maybe creating a new universe within it. It also ties into something called the holographic principle.
Holographic principle, like a hologram.
Sort of, yeah. It's this idea which came partly from studying black holes, specifically work by Jacob Bekenstein and later Hawking. They found that the information content, or entropy, of a black hole seems to be proportional to the surface area of its event horizon, not its volume. It's like all the information about what fell in is somehow encoded on the 2D surface. The holographic principle suggests, maybe this is true for the whole universe, that the information describing our 3D reality could be encoded on some distant 2D boundary.
That is profoundly weird. Black holes pointing towards a holographic universe.
It's a deep connection.
Yeah.
But coming back to whether our universe is literally inside a standard black hole, probably not.
Why not?
Well, the simplest reason is observations. Our universe is expanding, and that expansion is accelerating. It looks like it'll expand forever. Inside a black hole, as we understand it from general relativity, everything collapses towards a singularity and end of time. Our universe just doesn't look like the inside of a black hole. So, while the holographic ideas inspired by black holes might apply to the universe, this specific "we live inside one" scenario doesn't really fit what we see.
Got it. A crucial distinction. Okay, this has been incredible. We've gone from the basic idea, the river of space, the early math, to seeing their shadows, realizing you could maybe survive falling into a giant one for a bit, and even touching on holography. It's clear these aren't just cosmic vacuum cleaners, they're so much more.
They really are. They're cosmic laboratories, pushing physics to its absolute extremes. They force us to confront the deepest questions about gravity, space, time, information, reality itself.
Absolutely. It makes you think, doesn't it? Consider how these incredible objects, these gravitational titans, are not just about destruction. They actually reveal fundamental truths about the cosmos, about the rules of the game. They push the boundaries of what we thought was possible and keep opening up brand new questions about the very nature of reality.